Welcome, my name is Ramoso Cosmas. I'm going to take you through a review of optimal model complexity. For the contents of presentation, I'm going to take you through the introduction, the methods used for attaining an optimal model, and then the references. For the introduction, I'd like to talk about underfitting and overfitting, which are terms used to describe how simple or complex a model is. Most overfitted models tend to be complex, very, very complex due to the high bias. Hence, they fail to understand the underlying trending data because they are trained on a lot of noise in the data. And then underfitted models tend to be too simple. Hence, which is caused due to the high variance. Hence, they can't perform well on new data sets, because they were trained either on low data or usually they were trained on low data. So the goal is usually to obtain a model that's optimal in a way that it's in between. It's not too complex and it's not too simple. So there are numerous ways of attaining optimal model complexity, as we are going to discuss in the coming slides. One of these ways is ensemble methods. With ensemble methods, we mean you combine multiple weak models to produce better results. Perfect example of this, this is a random forest which combine multiple decision trees so that to produce a more generalized model. Ensemble methods utilize multiple machine algorithms to produce better results, and then they use several methods to fuse these results. One of them, as we've demonstrated here, is a method called voting. There is averaging. There are a lot of various methods, but as we see in this future, you see all these models, they came up with their predictions, and then the final result is based on a majority vote. And there's a method called averaging, whereby we would just average. We take the average of all these, where would be 1 plus 1 plus 2 plus 1 over 4. And then in some case, now this is for, I think, regression models. For cases of classification models, you can take the mode. Let's assume that the result here was maybe yes, here no, here yes, and then here yes. The mode would be yes, because yes was the popular choice with most of the models. So there's various ways of coming up with the final result after the weak classifiers have made a prediction. So this in turn usually produces a more accurate model, which is a combination of several weak classifiers or learners. The next method is feature engineering. Here we have to come up with new features from existing data. Usually these features can be generated using methods like transformation, where we use mathematical approaches like getting the logarithms, you can use the square, we can use exponents. So you have to come up with a way of coming up with new features using existing data. Perfect example of these, you might have temperature, and you realize that maybe the temperature in Celsius isn't doing it well, and maybe you come up with a new feature, maybe the temperature in Fahrenheit. Yeah, maybe another example is having the location of an employee, maybe where they live and where they work from. And then maybe you come up with a new feature like the distance they walk by calculating the geographical distance between the 2 points, since you have where they stand, where they work from. So you can come up with several features that describe the relationship that can help you make better predictions. Then for feature selection, here we have to make sure when you get a data set and you start pre-processing it, you tend to realize that there are certain features that are not needed in the data set, which slow down the model during the learning process. So you might remove these features and you end up with a very minimal data set with only the features you like. And usually you have to target features that are more important to the domain or to the main objective of the project. You have to target domain specific features. Getting a data set about an NLP model and it has an edge feature. An edge feature is useless to a parallel corpus. You have to remove that. You have to make sure that you trim down the model to only features you need and that are domain specific. And then a new method is another method is cross validation. With cross validation, remember when training machine learning models, we have to split our data into a training and then the test data. So in cross validation, we make sure that every observation in the data is used for both testing and training. You have to make sure that every observation you have in the data must serve those two purposes. We must train on it and also test on it. And there are several examples of methods of cross validation. There's the K-fold, leave one out, and then the Monte Carlo. But for this particular presentation, I'll go through the K-fold, whereby if we have like this particular example, we have like 6 observation, K-fold. With 6 observation, we can come up with three pairs. And if we have 3 pairs, it means we shall have 3 iterations. Our K is 3 in this case, which means out of the 3 pairs of data, which means x1 and x2, that's one pair, x3 and x4, that's a second pair, x5 and x6, that's another pair, which means we shall train on k minus 1, which means we shall train on 2 pairs. And then in each iteration, we shall be training on 2 pairs, and then we shall be testing on 1 pair. So the first iteration, we trained on x5 and x6, that pair, and then we tested on x5 and x6, and we trained on x1, x2, and then the other pair x3 and x4. In the second iteration, we trained on x1 and x2 and x5 and x6. Like I said, at a particular instance in time, you will train on k minus 1, which is 3 minus 1, that's 2. And then you test on 1 pair. So at the end of the day, you have to average, find the average of the test scores in each iteration to get the final prediction. So that's K-fold, which is a method of cross validation, and the entire goal is to achieve an optimal model. The other method is algorithm tuning. For machine learning development, we know that all the machine learning algorithms we deal with are parameter driven. And while we are tweaking around these parameters to achieve an optimal model, we must know their effect on the algorithm, so that by ensuring that we properly read the documentation, we have to understand, if I change this to this, how will the algorithm behave? The main goal is achieving a value for each parameter that increases the accuracy of the model. But to do this, you must know the meaning of each parameter and what set of values it takes in. Then the other point is treating missing values, and the other method, treating missing value and outliers. We acknowledge that while we are collecting data, there are mistakes made by both humans and then the machines. So these mistakes occur, and sometimes they lead to capturing of extreme variables, or you can call them outliers. These must be handled, And one way of handling that is imputing with mean, median, and mode for continuous variables. And then for categorical ones, you can treat those categorical variables, those missing variables as a separate category. Then for outliers, outliers can be removed from the data set. We can perform some transformations on the data to fill in these, to reduce the impact of these extreme values on our final score. We can perform transformations like getting exponents or getting maybe the logarithm, stuff like that, and then we make sure that we reduce the effect of these outliers on the final scores. Then the other point is adding more data. As you know, as you add more data to the the model will learn more and it will increase its accuracy. Although this has to be done carefully to make sure that we don't introduce noise into the data set, which might lead to overfitting. So we have to pre-process the data and we add more data to the model, and its accuracy will improve. And these are some of the references I used for this particular presentation. Yeah, thank you for listening.